I'm one of the organizers of the Dallas Blockchain um, Meetup group, and we are proud to be one of the largest, most consistent, longest running uh, blockchain meetup in Dallas, if not the largest, most consistent. But so thanks for joining and thanks for keeping it going. And one thing that I haven't mentioned in the last few meetings either is, if you have um, ideas on what you're working on or ideas or recommend a certain company to present at our meetup, we're always open and looking for good quality content to be presented. And which is what we have now with Michael and his series that he's put together. So thanks, Michael, for continuing to do this and going down this path. We get lots of participation and we get lots of good feedback and lots of interests. And it's always really good to uh, go back and look at the basics and even record the basics for posterity. And that's what's happening here. So thank you again, Michael. Um, and Juanel Mendez, who's also on the call, is one of the other co-organizers for this meetup, and she works with Thomson Reuters, who is our sponsor. So we continue to thank Thomson Reuters for making this possible. Um, and with that, I think I will turn it over to Michael and let him continue this session, the series.
All right. Thank you, John. All right. So let's go ahead and get to it. We got about 21 people, so I think we're good to go ahead and get started with the main content. So like John said, I'm Mike Lewellen. I do a lot of blockchain stuff here in Dallas. I'm sure you've been listening to the past conversations we've had and the other webinars. This is going to be on smart contracts and dApps, which we'll get into. I'm sure some of you are familiar with that. Some of you might be new. So I'm planning to make sure that the content is going to be interesting for either party. And we'll be kind of continuing our conversation from where we left off last time, which was on the rise of crypto assets. So we've looked over the history of money in Bitcoin to understand, what was first revolutionary about the technology. We've talked about how blockchain works, how it is able to secure transaction and makes them immutable, verifiable, and decentralized. And we also talked about the rise of crypto assets, where there's a lot of financial instruments and potential applications of blockchain in finance beyond just Bitcoin and digital cash. And now we're going to get, I think, into really where things get very interesting, where blockchain has kind of gone from just Bitcoin to blockchain in general beyond crypto to actually having a large, wide array of use cases. And so we'll be getting to that today, and it'll really, I think, set the scene for the next 4 talks we're going to have, because all 4 of those talks are going to dive a lot into how smart contracts are used. So this is really going to go over the basics of what smart contracts are and why they're important. So we've talked about blockchain beyond just payments and assets, but now we're going to talk about smart contracts. So what are they? What is a smart contract? What makes it smart? Why is it apparently so revolutionary? So smart contracts are innovative and very useful because they can automate trust by using blockchain properties to create what we like to call decentralized applications, or dApps for short. The idea being that this is a piece of software or an application that we're not trusting to any one third party. We can actually trust it to run in a decentralized manner, and that's what makes it so potentially impactful. So in this talk, to really go through what smart contracts are, we're going to cover contracts and computation, Ethereum and Solidity contracts, because Ethereum is one of the biggest platforms out there, so it will give us the best background. And even within the blockchain space, there's a lot of other options out there. Solidity and Ethereum continues to be one of the biggest, I would say the biggest players in this space. So it's always good to understand Ethereum first if you're trying to understand how blockchain smart contracts work. And to Sandcat, I will be making this available at YouTube, so I'll be sure to post that on Meetup once that's done. All right, so first let's dig into what contracts are and why trustless computation is important. So what is a contract? Contracts, I'm sure you're all familiar with this term, but I'm going to go over the basics as we usually do. They are agreements that govern the rights and duties of 2 or more parties and are often legally binding. That means that this is an agreement we have typically over something that you will provide to each other, And if you work in the professional business world, I'm sure you've seen a contract at one point. You've signed an employment contract. You've done contracts between businesses. You've signed contracts, I'm sure, paying for goods or services. There's many contracts throughout our lives. The most applicable of which we think of are, the ones where you sign on the dotted line, but there are even implicit contracts in terms of buying and selling a good at a store or many other things. But typically in the context of this conversation, we'll be referring to legal contracts, as in something that's legally binding. So a contract is typically around a good or service. There's other contracts, of course, but I think the most impactful is the one that is used for commerce, a commercial contract around someone providing service and then being paid for that service or good. And typically you see a lot of stipulations, very long documents that tell you what happens if a certain parameter or condition occurs, how you respond to that. If, for example, if someone's late making a payment, what is the recourse? Is there a late fee? Is there a certain amount of days that they have before there's a breach of contract? And then, of course, what is a breach of contract? What constitutes a breach? These are all things that, well, lawyers could spend a lot of time telling you about, but in this conversation, we're going to keep it simple. So here's a simple example. If Alice delivers goods to Bob, then Bob owes Alice a payment of $10. We can say that it's a cup of coffee. We can say that it's a widget. It doesn't really matter. It's a contract. And once Alice makes a delivery, the contract very clearly says that Bob needs to pay Alice. Now, what happens in the typical commercial world, if Bob decides to be an unfaithful actor and he refuses to pay Alice, well, with traditional legal contracts, there's no magic enforcement mechanism that happens. If Bob does not pay Alice, then Alice needs to seek legal remedies through the court system. And unfortunately, in the court system, despite the fact that it is a very strong foundation for capitalist society and very strong economies, it's still very messy for many commercial disputes. It's been estimated that global commercial contract claims resolved by litigation have cost upwards of $870 billion a year. And unfortunately, one thing this does is it prices a lot of individuals and small businesses out of the marketplace. It makes it very difficult for them to engage with larger parties that have more funding or a stronger will to litigate than they might, because ultimately, in many cases, it might not be worth the cost of litigation for a party to receive their payment, because it might, essentially be larger than that payment. So there's still a lot of inefficiencies in the way we do commercial litigation. Now, with digital commerce, we want a faster and cheaper way to enforce contracts and resolve disputes, because ultimately, there's a lot of potential out there for online commerce, and we've seen a lot of it grow over the past few decades. So the question is, how do we get that to scale? How do we scale disputes online? Well, one proposal that was made very early on is the idea of making our contracts smart, or in other words, as Nick Szabo put it in 1994, providing a computerized transaction protocol that executes the terms of a contract. So it does it automatically through a computer rather than relying on a piece of paper that we then have to bring in front of a court in order to actually make enforceable. And if you don't remember Nick Szabo, we actually talked about him in our first talk because he was one of the original creators of BitGold, which is a precursor to Bitcoin. So when he's talking about smart contracts in 1994, he's already thinking about it in terms in the context of a digital cash system. So the idea behind smart contracts are that they should be enforced automatically without an external party involved. You shouldn't need some third party to come in and resolve the dispute, either by ruling in one person's favor or by providing some external information in some way. So this doesn't just apply to blockchain, it also applies to any technology that kind of fulfills a contractual obligation. A point of sale system, if you go in front of a grocery store and you're paying for a good and then you're whipping out your credit card and paying for that, there are several contracts implicit in all of those actions in terms of paying for a good, your payment provider forwarding that payment, lending you money over the course of a month through your credit card that you'll eventually pay off. All of these things are kind of implicit contracts that you've either signed or implicitly agreed to. And so in a way, it's already very smart with the way we use technology today. Now, what Szabo saw with smart contracts was to go beyond this, was to use digital cash protocols backed by cryptography as the next logical step for how smart contracts will evolve. So And he thought this would be a great place to start because most contractual disputes arise over payments. That's usually the biggest sticking point in a contract in terms of someone creating a dispute. And if a digital cash protocol is already handling payments, adding smart contracts on top makes a lot of sense. So if we used a digital cash protocol here, when Bob is refusing to pay Alice, if it was a smart contract with access to a digital cash protocol, it might be able to compel Bob to make that payment, and basically it would mean that Alice would not need to go to through legal means to actually get that payment back. It would automatically be given to her. So ultimately, smart contracts are just another way of processing transactions, but they go beyond just validating payments. They also ensure that certain contractual conditions are met. So how do we compute a contract? We talk about this kind of conceptually, but what does it look like when we actually have to run one? Well, most smart contract transactions will follow an if this, then that process. Basically, if this condition is met, then this thing should occur. So an example would be if Alice delivered a good to Bob, then Bob pays Alice $10. That's a pretty simple concept, and it's something that is encapsulated in a lot of commercial contracts. It might have a lot more language around it and a lot more conditions, but in essence, that's typically how a commercial contract is going to play out. So let's take that example. Let's take that service smart contract, and let's pretend we've written that in code, a very simple code that just says if this, then that. And if this smart contract is digital, then the computation needs to be hosted somewhere. And you can typically host computer programs in two ways. You can do it on premise, which means you can run it on a local computer or on some server that you have owned by your company, or possibly running in your house if you're really into server home labs. Or you can run it on the cloud, which is a rented computer offered as a service, something offered by Amazon or Google or IBM. There's a lot of cloud providers. But in either case, that computer is controlled by a third party. So that computation might be modified to benefit one party over another if there's some sort of collusion going on. So let's say that Bob and Eve are very good friends, and Bob asks Eve to help him out. And when the smart contract is being resolved, let's say it's being hosted by Eve, she basically resolves it in favor of Bob and says that no payment is necessary, which is quite unfortunate because it means that Alice has basically been shafted and is no longer able to get paid for a good that she apparently had rightfully delivered. And Bob is just, feeling pretty lucky that he has such a good relationship with Eve. So this is, definitely, I think, a cute example. I think the actual issue of collusion is far more complicated than this, but it does give you the essence of the problem. If you're trusting someone else to run a program, then you're trusting that the program they're running is accurate and that they're not modifying the result when they hand it to you. So this is a very important concept to understand and why blockchains might be applicable for smart contracts. Instead of just running that software on a cloud, you might need to run it somewhere more secure. So with that, blockchain technology provides a very innovative solution to potentially decentralizing that trust to the point where we don't have to worry about this sort of collusion. So how do smart contracts look on a blockchain, and where did they actually come from? When did it actually occur? So Bitcoin was, I would say, kind of in a way, the first smart contract. It provides the ability to send payments from one person to another using Bitcoin. It has a bunch of rules built into the program that are smart, such as the fact that it limits the supply of Bitcoin produced. It adjusts the difficulty for mining over time. There's a lot of things that are smart about Bitcoin, but for the most part, it wasn't built to do just any smart contract. It was built to transfer Bitcoin. And even though people are able to kind of custom build smart contracts into Bitcoin, it's not built for smart contracts. It's kind of a building in that functionality after the fact. So despite the fact that some people have used Bitcoin for smart contracts, it's not always the best for that. And some early adopters back in 2010, 2011, like Vitalik Buterin, who was a writer for Bitcoin Magazine at the time, were proposing the idea of adding that functionality into Bitcoin. Let's add in a smart contract functionality that actually makes it easy for any developer to add a smart contract on top of Bitcoin. Now, many Bitcoin developers at the time did not want to do that. They didn't want to overcomplicate the protocol. They wanted kind of to stick to the main mission of being a digital cash protocol. So what Vitalik did is he actually went out, and apparently he got a $100,000 grant from Peter Thiel for being such a smart guy, because he is a very smart individual. And he went out and he published the Ethereum white paper as a proposal for a new blockchain protocol that would support custom smart contracts. And it would be the main mission of Ethereum. It wouldn't just be a cryptocurrency, it would be a smart contract platform. And what that platform would do, it would provide an ecosystem of decentralized applications that would use smart contracts to run on the Ethereum virtual machine rather than computation controlled by a third party. So a virtual machine in this case, it's just something that's simulated by the Ethereum blockchain as a machine that you can run software on rather than running it on AWS or a cloud service or even on your one computer. It is something that would run on the entire Ethereum network, and through that be far more trustworthy, because every single node that would run that computation and come to the same result would then validate it and make it immutable in the blockchain protocol. So it would host the code as well as the results. So this was a very innovative idea at the time in the terms of the way that Ethereum accomplished this. And it's one of the reasons that we still see Ethereum today. It has a lot of unique properties that were at the time very novel. And it's been adopted by a lot of other blockchain protocols since. So let's get into it. What does Ethereum smart contracts look like? And what do we see in terms of features that are new as opposed to Bitcoin? So Ethereum features include state storage. And this is actually something that's interesting when I discuss it with people, because some people have a concept of Bitcoin as the Bitcoin blockchain stores your account balance, in terms of if I looked into the Bitcoin blockchain and I looked at John, let's say I looked at John West's balance and it would say 10 Bitcoin. That's not actually true. It doesn't actually store account balances as state. That means as just, flat data. It only stores transactions. And so if I wanted to learn what John's balance was, I would have to calculate what's called his unspent transaction output, or UTXO for short. And that means I would take all the transactions that John has received, and then I would subtract all the transactions that John has sent, and that would give me his unspent transaction output, as in I calculate every time how many Bitcoins he still has left to spend based on what he's received and then sent. So in that way, Bitcoin is not there to store state. It's just there to calculate transactions. And then you can just calculate your balance on your own, which your wallet software will do for you, to figure out what you actually own. So what Ethereum does is it says we're actually going to also track state, because to track state will give developers a way to not only check balances far easier, because you can just check a balance instead of adding up all these transactions, but you can also store any piece of data that you might need to store as a result of a smart contract. So a transaction doesn't just store a transaction, it also changes state. And in some cases, you would actually call Ethereum a state machine. And in this slide, we're going to get a little computer sciencey. I'll give you all a heads up, but I think this is the most detailed and technical we'll get. But I think it's really important to understand these concepts, because it explains why Ethereum is unique, or rather was unique at the time. So in addition to state storage, Ethereum also changed the way that blocks were produced. It greatly increased the time, or I'm sorry, rather greatly decreased the time it took to mine a block. It went from 10 minutes to 15 seconds. And the reason it was able to do this is that, Bitcoin was originally doing 10 minutes because of the latency involved in mining. If I'm mining a block in the US and someone else is mining a block in China and I solve a block, it might take some time for that person over in China to learn that I've solved a block and he should move on to mining the next block. And if we move too quickly, if we have a very short block time, then he might fall behind the blockchain and might end up mining on a different chain that will confuse things and in general not be good. So what Ethereum does is it solves that problem by acknowledging the fact that some miners will mine on blocks that are not valid, just because they won't hear about it in time, but they'll still compensate them partially if they do solve a block that is, was kind of solved at the same time as someone else, and that's called an uncle. So basically, they get a small percentage, like 12% of the block reward, but it's enough that miners are able to continue providing services to the network and be fairly compensated while increasing the block time considerably. And Ethereum proof of stake and other potential improvements are also looking to decrease that time even more. So 15 seconds is far more usable than 10 minutes, because that's something that we can expect for a transaction to go through in a far faster time. We still like something faster, but it's definitely an improvement on what we had before. And then last, but certainly not least, is the concept of being Turing complete, the fact that Ethereum is a Turing machine. And for those of you who might not have gone through the Computer Science 101 courses that we computer science grads have, Alan Turing was a famous computer scientist that came up with a lot of the foundational concepts of computer science. He's considered kind of the father of computing. And one concept he had was a Turing machine. It's the idea that a machine can go through any kind of computation, anything you could possibly write down, any algorithm, given enough time. And the idea is that this machine should be able to do all the fundamental handle any fundamental algorithm you can throw at it. It's kind of like an all-purpose computing machine. Just like I might say that, let me think of a good example here, because it's actually it's an interesting topic. The idea that a language, for example, if I say something in English, there should always be something else in Spanish or French or German that roughly translates to the same thing. So I should be able to translate any sentence in English to any other language. And so we consider that a complete language, a fundamental language. In the same way, in computers, a programming language that is Turing complete, or a computer that is Turing complete, means that anything that you can write on that computer can also be written to run on any other computer that is Turing complete. And so that concept for Ethereum is important because it means that anything you write in a normal language like Python or Java to run on a normal program or a normal computer should also be able to run on Ethereum, given enough time and resources. And that's really important because it means that a developer can write code the same way he's used to on any other platform as on Ethereum, as long as he pays attention to certain requirements that we'll actually get into as we go through this more. But that's a really fundamental understanding. That's why Ethereum really changed the game. It said, we're going to make these smart contracts Turing complete for better or for worse, because it also means that there's a lot more complexity potentially involved in the smart contract. And so they're giving developers free rein to write what they want. And that does mean developers take a lot of responsibility for ensuring what they write is correct. And we'll get into that a little bit more. So let's look at Ethereum accounts, because this is a bit different now that we've introduced the concept of a contract. Because we know in Bitcoin that you just have a Bitcoin account. You have a public key and a private key, and you send Bitcoin back and forth to other accounts, and that's pretty much it. But with Ethereum, you actually have two different types. What you have is, first, in externally owned accounts for users. And this is pretty much the same as what you would see for a Bitcoin account. You'd have users, and they'll have a balance, and they'll have a public key that you can use to identify them. You'll be able to send transactions back and forth, either to users or to contracts. And you'll have a private key that allows you to control that account and determine what transactions are sent. So what's different about a smart contract? Well, smart contract accounts also have a public key, and they also have a balance. But rather than having a private key, they actually have code that determines how they handle transactions and how they send money back and forth. The way that this code is run is that it will be triggered by a transaction. So if Alice, for example, in the smart contract, and notice we put the same code in here as before. If Alice delivers good, then Bob pays Alice. And we have also put state in there, as in the state of the contract. And the state is that Alice has not delivered, in the state, and that Bob has not paid. So if Alice decides to submit a transaction that says, I have made this delivery and it is complete. So she's sending that as a transaction into the contract. And this transaction, despite the fact that it has some custom code attached to it, it has some code that it's trying to trigger, fundamentally it will work the same way as a payment transaction, the same transactions that we talked about in webinar 2. And so what happens when we send this transaction is that it will send it to the smart contract, and it will change the state. The state will be updated. And if you notice, Alice is now marked as delivered in the state, which means that the condition for Bob to pay Alice has been met. And we would now expect Bob to finalize that payment. So this is kind of a good rough example of what an Ethereum account would look like and how external accounts owned by users will interact with smart contract accounts. So let's get into my favorite part, which is actually writing a little bit of Solidity code. And for those of you who might have a little programming experience, what you'll see here is kind of a weird mix of Python and C and JavaScript. It's a fairly readable language with just a few weird quirks inserted in there. But we're going to go step by step and give everyone a chance to understand what we're looking at. Even if you haven't programmed before, I'll make sure that you have a good understanding of what's occurring. So what happens with a Solidity contract is that it is compiled down into bytecode and stored on the Ethereum virtual machine. And so any contract we write is callable by anyone else on the network. And so we always have to put conditions in to make sure that no one else can touch it. So let's go ahead and get started. So first we're going to define the contract. So we'll call this a delivery service. And it works kind of similar to class names and other languages. We'll just define a delivery service, and all the code for that delivery service, all the contract code will be within those two brackets. So let's define some state. Let's put out some variables that we're going to store in this contract. So the first thing we're going to do is we're going to create a Boolean value for Alice delivered. This is going to be either true or false. And in Ethereum, these values default to false if you don't set them directly. So we're going to assume that when we set that, it is now delivered. And you notice that public keyword that I put on Alice delivered, that basically means that this variable can be seen by anyone who looks at this contract. It's publicly accessible, and it automatically creates a function that anyone can use to access that variable and see what it is. So this will be useful later. The other thing we'll do is we'll define the address for Alice, and we'll say that it's 0x456 as an example. So we're going to mark that this delivery service contract will always refer to Alice as the person delivering the good. And then we'll also create another address that defines the buyer. So these are just storing the public key for Alice and the buyer, who in this case will be Bob. So once we've done that, now we have to do some setup. Now we have to define how the contract will start once it is created. And this is kind of like, you could say, defining what happens when someone signs on the dotted line. When this contract becomes active, what happens first? Well, in that constructor, we're going to make it payable because we would like Bob, the buyer, to provide his payment upon creation. So he's going to put that payment into this smart contract. The smart contract is going to have the balance. And in that case, the contract is going to hold that in escrow until a delivery is complete. And so first, we're going to put in a require statement. And what a require statement will do is it'll say, in order for this transaction to be approved, this requirement must be met. It's kind of similar to any contract requirement. And the important thing about this is this gets back to the way transactions work from webinar 2. Any transaction, if no condition is met, then the entire transaction rolls back. So a requirement must be met, and if it's not met, then the transaction does not go through and no state is changed. There's no modification to the blockchain. So in this case, we are checking to see if the message value, which is the transaction that Bob is sending when he creates this contract, is equal to 10 Ether, because that is the payment that Bob needs to provide for this delivery. So if Bob provides that in the contract, then we will record him, the message sender, as the buyer and store his address in the contract. So once that's complete, we now need to create a function to mark it as delivered. So this is a function specifically for Alice to mark when that delivery is complete. So you notice that we call it a function, and then we give an argument, which is called status. So basically, Alice will pass in the status as true or false. And then we'll put in a requirement that requires Alice be the only one that can call that function. So if Bob tries to call that function, or anyone else that doesn't have the same address as Alice, which is 456, then the transaction will be reversed. So only Alice can mark the payment as complete, or rather, I'm sorry, the delivery as complete. And then, if that condition is met, then Alice delivered will be marked as true. And that's actually a little typo there because I probably should have used the status. But in any case, if she marks it as delivered, then the variable Alice delivered will be marked true. And let's then create one more function, which is the send payment option, which is used by Bob to finalize the payment once Alice has made the delivery. So the first thing we're going to do is we're going to put in another require statement, and that is going to require that Alice has made the delivery. So if Alice delivered is true, then the requirement is met, and the message.sender is the buyer. So only Bob can call that contract. So if Alice has made the delivery and Bob is calling the contract, then we will transfer Alice the 10 Ether. So that's it. That's a simple smart contract that works on Solidity. And if you wanted, you could take this and run it. So let's do that. Let's give a quick example of what this looks like if we actually did try to run our own smart contract. So I'm going to pull up remix.ide. This is actually an Ethereum development environment that you can run in the browser. And it will simulate the Ethereum network so we can actually do some testing. So you notice here that I've got that same contract played out, delivery service. I put in a real address for Alice, and all the other code looks pretty much the same. So what we're going to do over here is we're going to see that we have an account defined 7D1, and we're going to say that this account is Bob, and Bob is going to deploy the contract. So once we try, let's hit deploy, and then what we can do is open up this here console and take a look. Oh no, it didn't work. VM error, revert. Why? Oh, I see. This requirement statement says that Bob needs to send 10 Ether in order for the contract to be created. And because we failed to provide that requirement, the contract didn't get deployed. So let's correct that. Let's put in 10 Ether and let's try again. Bam, the contract was deployed. Success. All right. So if that works, let's go on to the contract itself. So we can actually see the contract here. It provides two functions, the mark delivered and send payment functions, and as well as the variables. So we can look at Alice's address and get it back there. We can check the status of Alice's delivery, and it says false. And we can look at the buyer, who is Bob. So we have all that state stored on the smart contract, and it can be queried at any time. Yeah, Kevin, yeah, I know I needed to correct the Alice delivered true line. So right now it just automatically marks it as true. It doesn't pay attention to the status. Actually, why don't I'm just going to change that right now, because why not? A pretty easy one. So what I'll do is I'll change that, redeploy this, get rid of this contract, redeploy, bam. Okay, now we got a contract that has that corrected. Okay, so now that the contract is made and the contract has a balance of 10 Ether now, let's mark this as delivered. So I am going to go down to this function and hit mark delivered and hit true. Let's try to run it. Bam, we got another error. What could this be? Oh, I see. And I actually put a little error message in here. You aren't Alice. So it checked my account and it saw that I was not Alice. So let's change our account to Alice. Go down to 8AAA. Yep, that's the same one there. And then let's call that again. Bam, and it is now going through. That transaction is confirmed. And if I check the variable again, it is now true. So Alice's delivery has gone through, and that is reflected in the contract variable. Okay, now that that's done, we have got one more step, and that's sending the payment. So if I called this right now, it probably would fail because I'm not currently Alice. So let's go back to Bob's account, 7D1. And let's call the send payment function. So if we call that, the transaction does go through because Alice's delivery has gone through and we were calling from Bob's account. And if we look at the balances, we can see that Alice now has about 10 more Ether than she did before. So that's it. That is a basic Solidity contract and the way that you would interact with it on the Ethereum blockchain. If I wanted to, I could hook this up to the Ethereum network, deploy it, and it would work pretty much the same way, except for the fact that these transactions would take roughly 15 seconds or more to confirm. So it's a lot faster to show you this working with a kind of a virtual environment rather than the Ethereum blockchain, but the effect would be the same. So let's get into one question that might be on your mind, which is why is this 109.999999999 rather than just 10? Why didn't Alice get 110? Why is it lower than that? Why didn't the transaction include the entire amount? Well, that's because there is something called a gas fee. There is a transaction cost to sending these on the network. Yep, yeah, so in Tommy's case, it is the gas price. And so if we look at any of these transactions, we can see that there's a transaction cost as well as an execution cost. And that is defined in gas. So let's take a look at what gas is. And so we can pop right back over to this presentation and start talking our way through that. Let me go right back through this again and go into gas fee. So running Ethereum smart contracts aren't cheap because every transaction is computed by all other nodes on the network and they spend compute power to process and store the results. So they're not just storing these transactions, they're also running that code. That code that I showed you on the screen, if I put that on the Ethereum network, every other node will also be running it in order to test and make sure that they come back to the same result. So to incentivize these nodes and protect against spam, so basically to make sure that developers create programs that are efficient and don't waste compute, Ethereum calculates the cost of each transaction in gas, which is just a unit of measurement for each operation on the EVM, on the Ethereum virtual machine. For those of you who are computer scientists, this is actually all the way down to the opcode level. So every opcode in the Ethereum virtual machine corresponds to a specific amount of gas. And so for everyone else, that just means that every individual operation, every small operation that you can break up that the CPU is performing, or the virtual CPU, that has a very specific cost associated. So let's look at an example. Let's look at some math. So let's say we have a doMath function and it performs the following operation. It adds A to B, subtracts C, and then multiplies everything by D. Or if you went by order of operations, it'd be a little different, but you get the idea. And then it takes that whole result and stores it in E using the equals operation. So if we took that line by line and divided it into a gas bill to figure out how much it would cost to run this operation on Ethereum, we would get the following. We would look up the costs for each operation, and then we'd get a total cost of 14 gas. So that's how much it would cost us to run this on the Ethereum network. Now, every transaction is given a gas cost with a limit to be paid by the sender in Ether. So we take that 14, and then let's say that there's always the potential that some gas costs might not be estimated, and so we just basically want to say we don't want to spend more gas than 20. So it's kind of like putting a limit or a cap on the amount of computation. If you've used AWS before, it's like having a budgetary limit that makes sure you don't spend far more than you were expecting. And there's another thing that you have to add to that, which is the gas price, which is the price of gas determined by the market. So basically the gas price is kind of similar to Bitcoin transaction fees. They're market driven. So depending on how much the network's being used, it can go up, it can go down. But gas will always stay constant, which is why we have gas instead of just denominating everything in Ether. But the gas price tells you how much each gas unit will cost. And in the case of Ethereum, we don't price it in Ether because Ether is a very, very, if we price it all in Ether, then it would have a lot of zeros attached to it because these are very incremental payments. We actually price it in something called Wei, which is just a very small denomination of Ethereum. So if we took that gas price of 300 Wei and multiplied it by 14, which is the gas we're paying, we would get 4,200 Wei as the payment for this service. And another little tip, or rather a little Easter egg we had in our first talk, remember that there was another blockchain protocol in the 90s being discussed, created by a man named Wei Dai. And Wei, in this case, this unit of Wei, was named for him because of his early work in the blockchain space. So another little interesting tidbit about why it's called Wei. But if we convert that Wei into Ether to get an idea of what it actually looks like, we'd be looking at 0.000000. You get the idea of 42 Ether. So very, very small amount for this, but you can certainly add up the more computation you do to the point where you're looking at, most transaction costs can be anywhere from a few cents to several dollars. It depends on both what you're running and what the market prices are at the time. For example, right now on Ethereum, market prices are unusually high because of the amount of DApp activity with decentralized financial products. So you can definitely see it fluctuate over time. And there's actually several websites where you can go and you can look at that gas price being changed and get a good idea of what the market dynamics are. So it's a very fascinating component. And it kind of speaks to why Ethereum is a commoditized protocol, where it is commoditizing compute power, or rather decentralized compute power, and giving you a marketplace where you can buy and sell it. In the case of buying it, you're a developer and you're purchasing it. In the case of selling it, you're a node and you're being compensated for running it. Or in that case, a miner. So in this case, it's about a 1/100th of a penny, but can certainly add up. And so gas fees follow kind of a microtransaction approach in terms of how users are paying for their service. So rather than paying for the right to use the software license, which is typically a SaaS model, they're actually paying for the literal compute power it takes to run that specific operation. So you only pay for what you use. which is it's a very new way of doing things. It has both pros and cons, but it does provide some very interesting business models that were not previously possible. And so something to just keep in mind as a developer is that gas fees are typically going to be more expensive than normal computation. Anything you run on Ethereum will typically cost you less if you ran it on your own computer or on AWS in terms of the cost for the hardware and the electricity, etc. It's best to limit whatever program you want to write in a smart contract to things that require trustless execution. And that's always important to think about when you're getting into blockchain development and blockchain projects. Make sure that you focus on what blockchains are good at and leave everything else to the more powerful machines in terms of compute. So now that we've talked through smart contracts, let's get a little bit more into dApps and adoption. And I'll kind of start to answer some of the other questions that are out there as we get near the end of this talk. So what are some common Ethereum dApps that we can look at that gives us an idea of how this is actually being implemented? Well, one is probably the most famous that almost everyone of you will know about is the ERC20 fungible token standard. So this was a standard that came up in 2015 as a standard for creating tokens using Ethereum smart contracts. And so tokens are kind of like, they've kind of been likened to cryptocurrency, and they operate a lot like cryptocurrency. You use private keys to control them. You can move them around. They're decentralized for the most part, depending on the smart contract. But the idea is that anyone can create a token on Ethereum rather than creating their own blockchain protocol and creating a new mining network and all of that. You can actually build it all into Ethereum itself. And so a lot of people that were building projects on Ethereum, trying to build their own dApps, used ERC20 tokens to fuel an ICO. And so the ICO boom was really powered by this standard, by this ERC20 token standard. And it's really powerful because it is, even though you certainly need to know what you're doing, if you're a developer and this existing standard is out there and you can find a well-audited and well-used smart contract code that's already written, you can create a token with very little effort comparatively, deploy it, and then have access to all of the marketplaces out there that support ERC20 tokens. There are plenty of wallets that support ERC20 tokens. There are other protocols. Because it's an open standard, you kind of get a lot of other tools and functionalities in Ethereum, in the ecosystem, automatically just by using this common standard for a token. So that's one of the reasons that it's really blown up so much. And it's got now billions of dollars in market value being issued since 2015. And these are a few examples like Tether, Chainlink, USD Coin. Notice several of these are stable coins, which means they're tied to the US dollar. So they're actually using ERC20 tokens to represent dollars in Ethereum, which we'll get into a little bit more when we talk about DeFi. So another standard that's very famous because it kind of extended the same approach to another asset class, or rather another class of assets, is the ERC721 non-fungible token standard. And these were tokens that have unique properties. So where you have ERC20, typically every Tether coin is exactly the same. There's no difference between them. But with 721, every token is unique, and it has some sort of metadata embedded in it that allows you to understand what's unique about it and therefore allow you to discern some sort of unique value to it. So these are very useful for collectibles, physical goods, or even loans and derivatives, because those are very unique depending on payback mechanisms and other things like that. So ERC 721 really allows you to digitize real world assets because you have that direct link with metadata. And so you can digitize completely digital things, you can digitize physical things. When I was at Toyota, we actually digitized car parts using the 721 standard. So it's a great way to map over real world assets into the blockchain space. And then just like ERC20, you get a lot of support where there are marketplaces for trading 721 tokens that if you created a token, you'd automatically be compliant and could list your token there. So another good way to bootstrap any project or asset you're creating and issuing, you suddenly get this entire ecosystem that supports it. So last but not least, let's talk about something that's a bit more infamous, but still has a lot of use cases outside of one bad example, and that is a DAO, which is a decentralized autonomous organization. DAOs are basically used to autonomously run a group or manage assets using smart contracts. So you can allocate funds, you can resolve member disputes, and you can even provide governance based on someone's holding of tokens, such as ERC20 tokens. So This has, I think, a lot of potential, and you've seen a lot of interesting projects such as MakerDAO, another DeFi project we'll get into more, that have actually created organizations where people can create practically a decentralized financial system, kind of like a central bank for crypto that creates stable coins based on the dollar. But there has been one bad example that I think everyone hears about when it comes to the DAO, and that is the DAO hack of June 2016, where something literally called the DAO, which is the logo you see now, was hacked for up to $50 million worth of Ethereum. And it was hacked because of a security bug embedded in a smart contract that hadn't been caught, and someone was able to take advantage of it and pull a lot of money out. And this was a DAO used to do crowdfunding for Ethereum projects. And so there's a lot of money to be stolen, and it caused a very big rift in the community and also resulted in a hard fork. I think smart contract security has come a long way since then, but this is certainly still a risk that you have to be aware of when thinking about smart contracts that will handle financial assets, especially crypto assets. So with that, let's get into, I think, probably a really important part of this talk, which is what are the challenges? Like what's stopping us from adopting smart contracts for everything, or even for the use cases that do make sense. And really, I think some of those existing challenges include security vulnerabilities, like we just discussed. We need to make sure the contracts are secure. And in the case of what Ravi was asking in terms of how are disputes in smart contracts resolved, that's entirely left up to the code. The code will define how disputes are resolved. And if you have a dispute with the smart contract itself, in terms of you think the smart contract did not resolve if you didn't think it was resolved favorably, if you think you are still legally obligated to receive some sort of good or payment, then that's where you're still going to have a normal legal paper contract. So legal recognition and compliance is still a big struggle for smart contracts. And there's a few jurisdictions that have recognized smart contracts to some degree, but for the most part, they're not a wholesale replacement to legal contracts that we have today. You're still going to likely need to do some sort of dispute and governance outside of just smart contract code. And I think that's one thing that a lot of blockchain use cases sometimes get wrong. They sometimes think they can do everything with the code. The code will help, manage people and resolve disputes, and we'll all be happy. And that's ultimately not the case, but because of the potential for security vulnerabilities, as well as the fact that it's just very difficult to cover all of your bases. Sometimes you do need to go to a court to resolve a dispute. And then another thing that we're looking at as far as usability is the user experience and key management. So, that 15-second delay can still be pretty irritating to a user that's used to something that's within a second. So the 15-second delay to wait for confirmations can be a bit of a problem depending on the use case. Some use cases might be okay with 15 seconds, but others might want to have a faster response, as well as key management. So users now have private keys that they need to use to interact with these decentralized applications, these dApps. And so there are solutions such as MetaMask that will hold your keys in a browser through a browser extension that have, they've been working okay so far, but they have their issues, including security issues. And then you also have hardware wallets and other things like that, as well as centralized wallets that will hold your keys, but might have some issues that come up down the road. So key management is definitely a part that we'll need to figure out, as well as just general user experience. And then probably most importantly, transaction scalability and throughput. We do about a dozen transactions per second on Ethereum. And we've already seen that because it's a marketplace dominated by the way the gas fees are calculated, the more transactions that people are trying to put through, the more expensive it is. And so there is a scalability problem with both Ethereum and many other smart contract frameworks, because it's a decentralized system and it's never going to be as efficient as using something like a database or something else that's centrally hosted and managed. So there's a lot of solutions in play, such as layer 2 solutions that are trying to solve this transaction issue. But it's definitely one that I think we're going to continue to see for the near future, and maybe possibly for quite a while. I think it'll improve over time. We've already seen a lot of improvement, but overall, I think that's going to be a recurring theme in terms of improving scalability. So overall, smart contracts they challenge a lot of existing processes, and it's just going to take time and effort to truly adopt them. There's still a lot of potential, but we're likely not going to see smart contracts take over the world in the next year or two. It's going to be a very slow go. We can see this hype cycle from Gartner, And smart contracts in 2019, at least, were at the very tip of inflated expectations with a trough of disillusionment soon in the future. And I think we've already seen that. It already put ICOs at the bottom. It's kind of mixed a bit in this. This is a weird diagram because there's like a lot of things that smart contracts apply to that are at different stages as well. But overall, I think smart contracts have a massive amount of potential, but they have been overhyped a bit. And I think we're going to see a lot of productivity from them after that hype subsides. And I think we're already seeing a lot of interesting use cases that are getting traction. But overall, smart contracts are not going to be a replacement for every use case. They cannot replace legally binding contracts. You're still going to need those. Talk to your lawyers about how those works. And what we'll likely see is a smart contract is trying to implement a paper contract, or rather to help enforce part of a paper contract. But for the most part, if there's going to be a legal dispute around that contract, the paper contract is going to be the basis for which that is done, while the smart contract might be used to provide a history of the events within that contract. So maybe it can be helpful in contract disputes, but it's never going to fully replace paper contracts, at least not for a long time. It can't replace compute-intensive workloads. Like we said, it's more costly to use smart contracts than a normal program. So if you have something compute-intensive as a part of your decentralized app, it might be best to let a third party calculate that part rather than put it in a smart contract. Only really critical things like calculating, payments and marking things as delivered, that the sorts of things that are not very computation extensive but need some level of trust, those would be good use cases. It certainly will not replace databases and large volume storage. So despite the fact that Ethereum has the ability to store state, it's still not the most efficient way to do it. And in many cases, I think there's actually technologies like IPFS and other distributed file storage solutions that can work in tandem with smart contracts, where they will handle the bulk of data storage, and then they can link to a smart contract and provide the best of both worlds. But in general, you're not going to see smart contracts replace databases as a place to store data. This is probably the biggest headache I have with some clients, where they look at this as the new database that will be better than anything they had before. And unfortunately, that's just not the case. You will need standard good old SQL or NoSQL databases, but a blockchain is typically something that you'll use in addition to that if you have a lot of data storage needs, rather than replacing the actual data storage. And then last but not least, anything that can reasonably be done by a third party. If third-party trust is not an issue, if you're okay with AWS or some other cloud hoster making a calculation based on cat pictures or anything like that, then it's probably best you do that with a normal computer instead of a smart contract. Now, if you want to own that cat picture, or at least you want to have a marker that links you to that cat picture, say for CryptoKitties, which is one of my favorite 721 examples, you're probably going to want to use some smart contracts. But even the file itself, even the kitty cat picture itself, could be hosted on something like Amazon S3 for file storage rather than putting on a blockchain. So ultimately, there's always going to be things that third parties can do better. They can certainly almost always do it faster. So just always be aware that you need to be constantly asking yourself that question: can a third party do this, or should this be decentralized? Whenever you're trying to build a decentralized application, because even within a decentralized app, there are pieces that could be done by a third party. So, in conclusion, smart contracts have immense potential with their ability to combine computer automation, so automating a lot of currently manual tasks to validate parts of a contract, with the trust of blockchain technology. So that's really where we see a lot of innovation, is the ability to automate things without losing trust, because currently computer automation provides a lot of potential risks where the automation being done might not be trustworthy, or it might be resolving disputes in someone's favor that causes people to lose trust in the system as a whole. So overall, it has a lot of, I think, potential. And this is a good place to address Tommy's question, where he's asking about machine-to-machine communication. And I think that's a perfect example, because I think machine-to-machine communication is always something that I think humans are just always going to be terrified of, because of all of the Terminator movies we've seen, because we're always going to think, what is that computer up to? Even if we're not talking about a Skynet situation, the idea that a computer is talking to another computer and doing it rapidly and at a fast pace. And if we aren't able to see that in real time or put checks and balances into that, they might be making decisions that are not okay, and might not be restrictions around that. So a perfect example is stock trading. Most stock trading is now done by bots. It's done by bots on both sides of the aisle. I think it was like 70 or 80% of most stock trades are bots nowadays. And it's interesting because now you have bots trading against bots. And while I think there are issues that smart contracts can't solve cannot solve. There's always going to be something they can't solve. I do think the idea of like having those bots trade in a more decentralized and immutable marketplace that has a lot of ways for individuals to see the marketplace in real time in a fair way, I think that has a lot of potential. And we'll get into DeFi and some of the things that have been automated by smart contracts for both human to human, human to computer, and computer to computer communication. But yeah, I do think there's going to be a lot of potential for that. And as Tommy also followed up, like robo taxis and computing services in person, just like a point of sale system, they're going to, I think, provide a lot of value when smart contracts can integrate with physical automated machines and I think really jumpstart economies by doing a lot of work that doesn't add any value by having humans do it, which allows humans to then focus on other things that I think, in the long run will benefit economies on the whole. So since Ethereum launched, we talked a lot about Ethereum here, but there are many other platforms out there. Some of them are using very new techniques, both to scale or to provide better security or to provide better enterprise support. There's a lot of different ideas and techniques being used, but one important thing to note is that almost all these platforms still provide Solidity support. I think that pretty much everything I've listed, with maybe the exception of Neo, all provide Solidity support. So even though Ethereum might not always be the platform you build on, Solidity is a very dominant smart contract language in the current space. And so I think learning smart contracts with Solidity, at least at first, is definitely the way to go for the near future. So despite adoption challenges, smart contracts are still seeing success right now in finance and supply chain industries with some early projects. For example, we are seeing JP Morgan, who's creating the Interbank Information Network using an Ethereum fork called Quorum. So they have over 415 institutions across 78 countries involved. And for those of you who haven't been following recent news, there's actually a partnership between JP Morgan and Consensus, where JP Morgan is essentially, they're letting Consensus acquire their Quorum teams and project. And in return, JP Morgan is actually running a funding round for Consensus and doing some investment in their company. So lots of interesting things happening in the finance world. Another interesting tidbit that came out recently is that Starbucks is now providing blockchain-based coffee provenance using Microsoft's Ethereum platform. And I haven't really heard any details on that. I actually am linking that to a developing story because that came out literally yesterday. But a very good use case of blockchain-based coffee tracking to ensure that it's coming from the right farmer. And I've done actually some coffee supply chain projects with blockchain. I actually did my university capstone on that, so I'm very interested to see how that plays out because I think there's a lot of potential in that space. Santander, another finance project, issued a $20 million bond on Ethereum. So another interesting concept of financial projects. Gods Unchained, which is a trading card game built on Ethereum, allows players to both play games and own the cards they create. And if you know anything about trading cards or card collectibles and the value that some rare cards can hold, using a blockchain system to own those cards and then trade them has a lot of potential. I've seen a lot of people that get really into these sorts of things, and having it on a blockchain where they have a certain level of trust that they own that product and that the company that issued it or the developer that issued it or whoever issued it will have some sort of restriction on supply or anything like that. There's a lot of potential there, I think, and we're going to continue to see, I think, the video game industry and video game collectibles and items embrace kind of the ERC 721 standard more and more. And then finally, and leading into, I think, what we'll be talking about next time, stable coins in decentralized finance are probably one of the biggest success stories when it comes to smart contracts. and they now hold billions in asset value on the Ethereum protocol. I'm showing you a few examples on the screen now that we'll get into later, but suffice it to say, these are very interesting products. They are providing ways for people to do decentralized margin lending on Ethereum, to create stable coins that are tied to the US dollar, that are allowing people to earn liquidity on their Ethereum assets, and something that they're calling yield farming, which I think is very fascinating given the lack of, the very low interest rates we have in this current environment. It's interesting to see that DeFi is offering an alternative to boost yield performance that is currently very difficult to find in traditional markets. So overall, I think we're going to see a lot of potential from smart contracts in the future, and can't wait to talk more about how they work with decentralized finance next week. So before I answer some questions, just some quick links to check out. And I'll post this, a link to this in the chat for this presentation, so you can actually get to these links yourself. But first of all, my company has a new website. Our designer, Justin, has put a lot of hours into creating a new version. So we're happy to get any feedback you have. And if you want to look at past talks, we're actually going to be hosting our talks there. So, or rather, we're hosting links to both upcoming talks and the previous talks that we're putting on YouTube. So that's a great place to look at if you want to get a lay for what talks are out there and what's coming up. And then another thing to be aware of is that next week we're going to have Dallas Startup Week, blockchain track. I'm going to be hosting a panel with Mance Harmon from Hedera, Hudson Jameson from Ethereum, Paige Krieger from IBM, and Kieran James Lubin from BlockApp. So it's going to be a really interesting panel because it's going to have people from the Ethereum space, from the IBM blockchain space, from the Hedera space, with very different views of public and permissioned blockchains. What makes sense? How do we scale it? I think we're going to have a lot of interesting conversations there. So I hope you show up for that, as well as several other events that we'll have, including seeing Lee Bratcher from the Texas Blockchain Council talk a little bit more about the Dallas community. And then last but not least, if you want to learn some Solidity smart contract programming, check out cryptozombies.io. They have a very interesting gamified mechanism for learning more about it. So let me send that link for the drive so you can get an access to a PDF copy for this presentation. And let's get into a few questions. 102. So I would say I finally finished before time was up too much. So let me address the question from Suman. Oh, actually, it's more of a statement, but health industry will be greatly benefited by smart contracts, and even insurance. Yes, I think I've worked on a few insurance projects, and I think that's going to be a very big space for blockchain to be playing in. And I know that there's several insurance providers already looking into it. And yeah, the fact that I think what you can do is offer insurance projects. Like I worked on a project called TandaPay, where they were allowing individuals to create their own insurance pools, where people could put money into a pool and then pay out to individuals that has certain claims. So it provides a lot of interesting alternatives to traditional insurance, as well as, I think, ways to optimize current insurance companies and the way they do business. All right, I think someone else has unmuted. Is someone looking to ask a question? I don't know who's unmuted.
I unmuted.
Oh, okay.
Any questions? That was really good, Michael.
Thank you.
And I very seldom call smart contracts anymore. And part of it's because of what you alluded to, of what you're going to talk about next in the DeFi space. I mean, it's programmable money.
Yep.
So it's code, it's programmable money. And then, or just even the ultimate vision of Ethereum, be the world computer, but which isn't necessarily a good name, but you mentioned it before, but decentralized compute, or decentralized code. It's a way to run code on many computers versus smart contracts is so misleading. But anyway.
Yeah. I think
Really
what
good
Nick Fable said was good. In terms of, it's like, anything could be a smart contract if it's like fulfilling a contract with a computer. So it's like blockchain smart contracts are kind of more of a specific thing, but we always mean blockchain now when we say smart contract. So I agree. The terminology is getting a little weird.
Well, thanks everyone for joining again, and tune in 2 weeks from now.
All right. Thank you all. Looking forward to it.
Goodbye, all.